Okay, thank you for the introduction. I'm Atsushi Okazaki at RIKEN, and I'm working with Takumi Honda, Shunji Kotsuki, James Taylor, and Takemasa Miyoshi. I will talk about radar data assimilation in this talk. Well, let me introduce the background first. So the TRMM, TRIM, PL, and GPM, DPL have been important platforms to provide a direct measurement of three-dimensional precipitation structure globally. So building upon the success of them, JAXA is now planning next generation rainfall measurement satellite. And one of the candidate is geostationary satellite-borne precipitation radar, GPR. And the aim of this study is to investigate the impact of GPR for the weather forecast. And as our first test, we investigate a typhoon case. So this is the image of GPR. So the GPR consists of Ku band precipitation radar with active phased array elements functioning. And the horizontal resolution of the beam or radar is limited by antenna size. And JAXA now estimated that 20 meter by 20 meter antenna is the maximal size. And this size of antenna achieved 20-kilometer resolution at the nadir and 500-meter range resolution. So what kind of observation GPR can get? What is the pros and cons of that? So the advantage is that it can measure precipitation almost continuously. That is a big advantage against low Earth orbiting satellite like TRIM or GPM. And however, there is also disadvantage. One disadvantage is that its resolution, horizontal resolution, or the sampling volume is relatively large compared to GPM, DPL. It is 5 kilometers, and GPL is 20 kilometers. And the second disadvantage is that when GPL sees of nadir points, the sampling volume must be tilted against the Earth's surface. So these 2 points should result in severe ground clutter. So that is disadvantage. And so we examined what kind of observation GPL can get using simulations. And in this simulation, radar received power from precipitation is simulated based on joint simulator developed by Masunaga and Kumero. And radar received power from the surface is modeled following Wentz et al. 1984. And they provided the model for normalized radar cross-section, sigma 0, as a function of surface wind and also the incident angle. And when you see this graph, the normalized radar cross-section becomes smaller along with the incident angle or the off-nadir angle. And it also, on the other hand, it increases along with the speed of surface wind. And to understand the characteristics of the radar observation, we first showed the results from an idealized case in which we assumed that the atmosphere below 2 kilometers is filled with a certain intensity of precipitation ranging from 1 millimeter per hour to 60 millimeter per hour. And the second assumption is that the surface wind speed is assumed to be 10 meters per second everywhere. And the figure shows the shading in the figure shows that signal to clutter ratio noted by S by C in altitude, latitude coordinate. And the clearer, the larger the ratio, the larger the value, the clearer the signal is. So red is good, blue is bad. For weak rain, signal is available only at nadir and only for high latitude. When the precipitation is strongly enough, the signal can be available for all area, almost everywhere. Then we next examine the real case for Typhoon. So these figures shows the precipitation reflectivity. This is nature, and this is the case with beam resolution of 20 kilometer, and this is the case with 20 kilometer beam resolution, but the sampling span is 5 kilometer and oversampling case. And this is the 5 kilometer case. As you can see that when you use the 20 kilometer beam, the pattern is highly discretized, and when you see the gray zone, the shape of Typhoon is largely different from nature run. And so this is the case of 20 kilometer. And when if we can use 5 kilometer resolution beam, the pattern is quite similar to the nature run, and also the value is also very close to the nature run. And when you make a slice here, the pattern, the cross section is like this. The hatched area shown is that the signal to crater ratio is higher than 0, and we say that we refer to that area as the highly crater contaminated area. And when you see that area with the beam, with a case with 20 kilometer beam resolution, the crater height will be around 7 to 9 kilometer height. But if you can use 5 kilometer resolution beam, the crater height will be less than 5 kilometer or less than 3 kilometer. So that's the image of the observations. And next, we investigated what will happen if the observations are assimilated. So in this experiment, we investigated this question in the framework of perfect model OSSE. So, and our case is Typhoon Soudelor 2015, which was the strongest typhoon in this year. And for the observation, as a first trial, we assumed that the radar resolution is 20 kilometer and also sampling span of 20 kilometer. And the observation frequency was assumed to be 1 hour, and the observation error was 5 dBz. So we use SCALE-LETKF system developed by Lien et al., and the ensemble size was 15 member. And for the localization, I set 100 kilometer for horizontal and 2 kilometer for vertical. And the outermost boundary condition is NSF-GFS, and domain 1 was conducted in 15 kilometer resolution, and domain 2 was 3 kilometer. So the nature run starts from July 28th for domain 1. Oops. And nature run for domain 2 starts from July 27th. And the experiment starts from July 20, and the initial conditions are up from arbitrary date of NSF-GFS. And up until July 28th, the real prep buffer is assumed to be domain 1. And for the latter part, the prep buffer created by nature run was assimilated. And for domain 2, observations are created by nature run domain 2 and assimilated from, August 1st. This is my experimental design. So let's move on to the result. So these figures shows the reflectivity pattern for nature run and analysis in first guess at first data assimilation cycle. So compared to the first guess, the pattern of the reflectivity in the analysis is much closer to the nature run. So it confirms that the data assimilation system worked properly. And after the first cycle, the analysis and the forecast both closely follows the nature run. And as you may notice that the pattern is bit spread compared to nature run, but this is because I showed here is ensemble mean. So yeah, please note that. So how about the Typhoon minimum sea level pressure and its track error? So the figure shows minimum sea level pressure and track error for two cases. One is GPL without clutter and the green line is for with clutter. In the case of without clutter, all the observations are not contaminated by clutter. So in the case of the red line, there is no ground clutter at all. So when you see the right figure, in the both cases, the track intensity are well analysis and also focused. Oh, by the way, the thick line shows the analysis and thin line shows the focused. So both experiments succeeded in simulating deepening in this case. And when you see the track error, the analysis will simulated the typhoon position, but when the focus starts, the track error grows very quickly. And two features are apparent from the figure. One is that the green line, I mean the case with clutter, is better than the case without clutter. This is a little bit interesting or surprising because that the number of observations in the green experiment is smaller than red one. And also, as I said, when the focus starts, the track error grows rapidly. That is also a point we have to investigate. So I investigated those 2 points. So the first one, why GPR with clutter is better? The answer to the first question is that the reflectivity at lower altitude is detrimental. So this figure shows the correlation between reflectivity and humidity in the altitude correlation coordinate. So for the lower atmosphere, the correlation is very small, almost 0. So if you assimilate the reflectivity here, the RMSE increase. So it shows that the analysis assimilation of reflectivity at low altitude is detrimental. But the correlation is high for the middle or upper troposphere. The RMSE decreases in the analysis step, so that's reasonable. So, and what I want to say here is that the answer to the first question is that the reflectivity at lower atmosphere is detrimental, and better result, not assimilating those detrimental observations, is reasonable. That's the first point. And the second one is why track error grow quickly in the focused. Again, I calculated the correlation between reflectivity and wind field, and as you can see, for every height, the correlation is very small. So we cannot expect good track error in the first place with assimilation of reflectivity because the assimilation does not have a power to constrain wind field. And the second, we found bias in the boundary conditions. This shows the bias in westerly field, wind field, and you can see that there is a bias, westerly bias here, which forced Typhoon to stay the same point. So this is the cause of the large track error in the Typhoon. And when you substitute the boundary condition to that for truth simulation, the bias is mitigated. And also, I used this true boundary condition and I simulated radar reflectivity. The focus was decreased. So the substituting boundary condition results in better track focus. And the message here is large track error is not because of GPR assimilation, but because of the boundary conditions or maybe initial conditions. So, and finally, I want to discuss something. And the previous study done by Lien and Shea, 2013, shows that assimilation of radar reflectivity fails to produce deepening of tropical cyclone. This line failed. But in this study, we succeeded. What's the difference? So first of all, the experimental setting is totally different. They used observation, and ours are perfect model OSSE. Because in the experiment using real observation, there must be many biases, like model biases or the bias from observation operator. So it is difficult. And I have to admit that ours are much easier problem. But here I want to focus on another point, that is resolution of the radar observation. They assimilated observation of like 1 kilometer resolution or so, but ours are 20 kilometer. And because ours are very large observation volume can mitigate non-Gaussianity through central limit theorem. So the figure shows the observation minus focused histogram, and these figures are created by using the resolution of 3 kilometer, and this created by the resolution of 30 kilometer. And qualitatively, the pattern is like Gaussian in this pattern. So maybe we are not validated fully, but the results suggest that, again, large observation volume may mitigate non-Gaussianity. And yeah. Okay, let me summarize. So we evaluated the potential of GPR for a Typhoon case, and we demonstrated that the GPR has a potential to improve focus for Typhoon intensity. And results suggest that GPR assimilation may benefit from its relatively large sampling volume through central limits theorem. Thank you very much.
So thank you, Atsushi. We do have time for